անգամ սկսում ենք մեր սեմինարների շարքը Վահանի ձգույթով, Մկրտչյան Վահանի, մեր նախկին շրջանավարտներից, լավագույն ուսանողներից կիրառականի, հետագայում իհարկե ինքը շարունակեց postdoc անել Գերմանիայում, հետագայում Կանադայում, եթե չեմ սխալվում, հետո Իտալիայում, ու այս վերջերս հայտնվեց Բոստոնում, ինչքան իմացանք, մի վայրկյան մեր ուսանողներն էլ են միանում, մի վայրկյան, ընդ որում տարբեր համալսարաններից, մի րոպե։ Շատ լավ, Վահանը զբաղվում էր և իր թեկնածուական աշխատանքը նվիրված էր հատուկ տիպի զուգակցումներին, որի վերաբերյալ բավականին հետաքրքիր արդյունքներ էր ստացել ժամանակին, հետագայում ինքը ընդլայնեց հետազոտությունների տիրույթը ոչ միայն ուսումնասիրում էր զուգակցումներ, հատուկ տիպի, այլ նաև արդեն սկսեց ուսումնասիրել կողային ներկումներ, ֆլոուներ, հոսքեր, և հիմա ինքը կներկայացնի իր վերջի արդյունքները նորմալ կողային ներկումների, խորանատ գրաֆների, նորմալ կողային ներկումների մասին, ես կարծում եմ ավելի մանրամասն կներկայացնի Վահանը դետալները։ Վահան, համեցեք։
Շնորհակալություն, ես սկսում եմ, ուրեմն ժողովուրդ, ես լինքը share եմ արել կոլեգաներից հետ Իտալիայից, ու Giuseppe-ն խոստացավ share անել նաև իր կոլեգաների հետ, այնպես որ հնարավոր է, որ ինչ-որ ինտերնացիոնալ կազմ լինի մեր սեմինարի ժամանակ, այնպես որ ես մեծամասամբ խոսելու եմ անգլերեն, իմ սլայդները անգլերեն են, բոլոր այն ուսանողները, ովքեր որ եկել են Պետրոսի հետ մեր սեմինարներին Հայաստանում, ես իրենց խնդրում եմ, որ ինձ կանգնացնեն ու հարցեր տան սկսած տերմիններից, թե մեր հայտնի զուգակցումները կամ հոսքերը ոնց են դառնում անգլերեն լեզվով։ Ես ստիպված եմ անգլերեն խոսել հայկական հյուրընկալության տեսանկյունից, էլի։ All right, so basically I'm going to discuss one of my recent results about cubic graphs that I got with Giuseppe when I was visiting the University of Verona in 2017-2018. So basically, here's the outline of my talk. I will start by presenting some conjectures in graph theory. Then we will move to the discussion of normal edge colorings of cubic graphs and why these type of colorings are important. Then I will present our result and try to somehow give you a glimpse of the ideas that we used in order to obtain the result. Finally, I will present one open conjecture that Giuseppe, I, and some of our colleagues feel that this conjecture needs to be proved. So, as usual, I have a habit of starting by presenting my collaborators. So my collaborator within the frame of this work is Giuseppe from University of Verona. So let's start with presenting some conjectures in graph theory. So since my talk is aiming not only for graph theorists, I will start from the very beginning. So let's try to give the definition of a graph. So basically, what is a graph? Usually, I will denote graphs with capital G, and a graph for us is a pair which we will denote by V and E. But basically, V is of any finite set. The type of elements will not be important for us, and E is a list of pairs of the elements from capital V. Basically, it is just a list, and they may be repetitions, and the order of pairs in each pair is not important for us. In graph theory, we have a habit of referring to capital V as the set of vertices, and its elements are called vertices, and capital E represents the set of edges of the graph. Now I would like to give an example of a graph. So let's assume that our capital V is the set ABC plus one, and the numbers 1 and 2, and let's assume that capital E is the following list of pairs from V. Then basically G is a graph. As you see, if this list is a bit long and V is a bit large, then this way of working with graphs is not that easy. That is why we have a habit of somehow drawing a graph, and we usually do that in the following way. So for each vertex, we draw some point, and we join points by a line if the pair is an edge in the graph. So for example, in this example, I have two sets which correspond to the pair 1, 2. That's why I have two lines connecting 1 and 2. Similarly, I have two pairs of BC. That is why we have two lines joining the vertices B and C, and I have one line joining AB and AC because this pair appears only once in our list E. As you see, the lines sometimes are straight, sometimes are not straight. I just want to make clear that the topology of the line is completely irrelevant for us. We absolutely don't care how the line is drawn. The only important thing in graph theory for us is that the pair is present in capital E or is not present in capital E. Now, as you see in this example, our graph is comprised of some two components. I don't want to define this component precisely. It can be done in a very beautiful way, just using equivalence, equivalence classes that just defining an equivalence relation, and each component will represent the equivalence class. But sometimes in my talk, I will discuss this connected component. In this case, for example, for the case of we have two connected components. I think it's more or less intuitively clear what is a connected component in the graph. So here, I just want to say that 1, 2, and BC will be called, will have multiplicity 2. It means that there are two edges joining them, and they represent multi-edges or parallel edges of the graph G, and the remaining two edges are our simple edges in this graph. Okay. Now, paper graph theory is making clear what is a graph. Basically, a graph. I mean, the definition of a graph varies from a paper to a paper, so you have to make it clear. So in this talk, we allow parallel edges, though there are papers that do not allow more than one edge between a pair, and also we do not allow loops. Basically, what is a loop? Sometimes it's convenient to have an edge that joins a vertex. In this talk, we will not assume that our graphs contain loops, so there are no loops, but they could be many parallel edges. And for the particular case of graphs, when each edge has multiplicity 0, each pair has multiplicity 0 or 1, in this type of graphs, we will refer them as a simple graph. An important notion in graph theory is the degree of a vertex, which represents the number of edges that this vertex is incident to. Roughly speaking, this means how many lines are going out of the vertex. So if we go back to our example, on the left, in the left component, these two vertices have degree 2. In the component in the right, the one vertex has degree 2, and the other two vertices have degree 3. An important notion for my talk will be the notion of a cubic graph, which represents a graph where each degree is 3. And we will say that a graph is k-regular if every vertex has degree k. So because are just 3 regular graphs. A graph will be called KH colorable if its edges can be colored with K colors such that adjacent edges receive different colors. So basically any pair of edges that share a vertex must receive a different color. And the smallest K for which our graph is KH colorable is a well-known concept in graph theory. It's called chromatic index of G, and sometimes it is denoted by G prime G. So if we look at our example, then you will see that this graph has chromatic index 4. Why this is the case? Because if you look at the coloring that I have put for you, then this is a proper 4 coloring. This is a 4H coloring. On the other hand, the component in the right, any pair of edges are adjacent, so they have to receive different colors in any KH coloring. So you have to use at least 4 colors. And since I succeed with 4, it means that chromatic index is 4. We will not need these theorems, but I really would like to share it with our colleagues who are not experts in graph theory. So I would like to present the theorems of Shannon and Wiesing. So an important notion for graphs is the maximum degree of a graph, which is just the maximum degree of a vertex in G. And mu G will denote the maximum multiplicity of an edge. So basically, which of the edges has the maximum possible multiplicity in the graph? It will be denoted by mu G. So the classical theorem of Shannon says that no matter which graph you take, its chromatic index is going to be between delta G and 3/2 delta G. And there is the theorem of Wiesing, which says that this number should be between delta and delta plus mu G. In particular, when mu G is 1, it means that we are working with simple graphs. This bound becomes very interesting in the sense that chromatic index is going to be between delta G and delta G plus 1. So it is either maximum degree or maximum degree plus 1. If we go back to our example, then here maximum degree is 3, maximum multiplicity is 2, and chromatic index is 4, as we discussed before. As you see, chromatic index can be smaller than delta plus mu, which is guaranteed by the theorem of Wiesing. So it can be smaller. Also, chromatic index can be larger than maximum degree.
Yeah, Vahan, I'm sorry, but the maximum degree plus 1 is almost like a, this is the edge coloring, sorry. Okay, yeah, sorry, go ahead.
Okay. One of the corollaries of the theorem of Shannon, which was presented in the bound with 3/2 delta, basically it implies that if you have a cubic graph, then its chromatic index is going to be between 3 and 4. And at some point, I was very surprised to see that this result was published before in some journal of American Mathematical Society. Unfortunately, I do not remember the name of the author, but I want to say that this result was proved before the 2 general results that I mentioned. So for cubic graphs, chromatic index is going to be between 3 and 4. And I just want to share the classical theorem of Hollier, which says that if you want to characterize the graphs, the cubic graphs for which chromatic index is 3 and the remaining cubic graphs have chromatic index 4, then this problem is a terribly hard problem from the perspective of polynomial algorithms, in the sense that this problem is NP-complete. Those of you who have never had a chance to deal with computational complexity just assume that it's very unlikely that there is a polynomial algorithm which will say that whether a given graph has chromatic index 3 or 4. Now, let me define the notion of independent edges and matching. So 2 edges in a graph will be called independent if they do not share a vertex. This means that they are not incident to the same vertex. And a matching for us will be a set of independent edges, basically a subset of edges, such that any two edges do not share a vertex. A maximum matching is a matching that has maximum size, and I hope you see that any matching in any graph can have size at most v/2. V is the number of edges because each edge joins just two vertices and they cannot share a vertex. So any matching has cardinality at most v/2. In this magical case, when it is exactly v/2, then such a matching is called perfect. And as it is not hard to see, any vertex of a graph is incident to an edge from a perfect matching. So basically, perfect matchings are the type of matchings that cover all vertices of the graph. Here I have brought a very simple example for you. This graph is the path with 5 edges or 6 vertices. The two red edges, I hope you see these two red edges, they represent a matching in this graph. As you see, this matching is not a maximum matching because the 3 edges outside these matchings form a larger matching, and actually it is a perfect matching in this graph. Another important example for us will be the complete graph on 4 vertices. Basically, a graph is complete when every pair of vertices form an edge in the graph. So the complete graph on 4 vertices is usually denoted by K4, and as you see, it is a cubic graph. And in this graph, I have brought an example of a perfect matching. The diagonals in blue form a perfect matching in K4. An important notion for us will be the notion of a bridge. Basically, what is a bridge? Bridge is an edge which if you remove, then you will have more connected components than the original graph does. So if we look at this cubic graph, as you see, this is a cubic graph, then it contains only one bridge. I have denoted it by small letter E. And why it is a bridge? Because if you remove it, then you will have two components which are not related. So that is why E is a bridge in this graph. And it is not hard to see that an edge is a bridge if and only if it does not lie in a cycle. And the remaining edges are not bridges in this graph. So this cubic graph has only one bridge. Why the notion of bridges are important? There is this classical theorem of Petersen, which says that any edge of a bridgeless cubic graph belongs to a perfect matching. So for this restricted type of cubic graphs which do not have a bridge, it turns out that every edge belongs to some perfect matching. Basically, each edge can be extended to a perfect matching of the original graph. And this result prompts the following definition that we can, for bridgeless cubic graphs, we can define kg. I denoted it in kg, and some people use different letters. So it is the smallest number of perfect matchings that using which we can cover the whole edge set of the graph. Basically, what is the smallest number of perfect matchings of the graph that you need in order to represent the set of edges as a union of these perfect matchings? Okay. Now let's try to understand this observation. It's really very simple, and one can easily see that if we have a cubic graph, then its chromatic index is 3 if and only if this parameter kg is 3. So one direction is easy. If chromatic index is 3, then you can partition your you can color this cubic graph with 3 colors, and since each degree is 3, then each of the colors has to be present around each vertex. So you have 3 perfect match. You have partitioned the edge set into 3 perfect matchings. That is why kg is 3. On the other hand, if kg is 3, then you have represented the set of edges as a union of 3 perfect matchings. And since the graph is cubic, they cannot have an intersection. That is why chromatic index is 3. So you see that chromatic index and Kg coincide when we have a 3H colorable cubic graph, and they are different when the cubic graph is not 3H colorable. And the smallest example for which this holds is the classical Petersen graph, which will be very, very important for this talk. And I want to show it to you. Those of you who work in graph theory, of course, know Petersen graph, but for non-professionals, I mean, it would be really beneficial to see this graph at least once in your life. So this is the Petersen graph, which is the smallest bridgeless cubic graph, which is not 3H colorable. And it can be shown that its chromatic index is 4, and actually there are papers that come up with new proofs for this fact. So I just want to say that this graph is very important, and people still prove that its chromatic index is 4. If I recall correctly, once we discussed a proof of this in our seminars in Yerevan State University. Now, it turns out that the Petersen graph has 6 perfect matchings, and these 6 perfect matchings have a magical property which I want to discuss. So it has 6 perfect matchings and it has 15 edges. If you count, you will see that Petersen graph has 15 edges and 6 perfect matchings. Now, the key observation is that with these 6 perfect matchings, that you can make 6 choose 2 pairs, and 6 choose 2 is exactly 15. And I hope you already see what I'm going to say, that for each edge there are 2 distinct perfect matchings for which the intersection of these 2 perfect matchings is exactly this edge. In other words, each edge you can come up with a bijection in the Petersen graph by making a correspondence in the sense that each edge corresponds to a pair of distinct perfect matchings. And this fact actually can be used to show that the K of the Petersen graph, the smallest perfect number of perfect matchings that you need in order to cover the Petersen graph, is 5. On the other hand, as I said, that its chromatic index is 4. So here K exceeds chromatic index. Why these parameters are important? Because they lead to some conjectures which were somehow posed in 1970s, and they are still open, and I want to discuss them. So the first of them is a conjecture due to Berge, which says that for any bridgeless cubic graph, Kg is at most 5. Basically, the idea is that up to now, no one was able to come up with a better, with an example that has larger K than the Petersen graph. So Petersen graph has 5. No one is able to find something where K is larger. So here is a conjecture that it should be at most 5. There is the next conjecture, which is which one of from Italy, not Giuseppe, once referred to this conjecture as something like a magical conjecture. It says that any bridgeless cubic graph should contain 6 perfect matchings, such that each edge of your bridgeless cubic graph belongs to 2 of these perfect matchings. Roughly speaking, for each bridgeless cubic graph, you can find 6 perfect matchings, such that each edge belongs to exactly 2 of these perfect matchings. Basically, why people are interested in this conjecture is the following. If you want to cover the edge set of your bridgeless cubic graph with 3 perfect matchings, then each edge should belong to exactly 1 of them. And as Petersen graph demonstrates, there are examples where you cannot do this. Now people want to do the next step. Okay, we cannot get 1 everywhere. Can we get 2 everywhere? I mean, each edge gets frequency 2. So this is the magical property that Berge-Walkerson conjecture tries to achieve, and up to now it is open. And another way of stating this conjecture is the following, which you may like. It says that if you have a bridgeless cubic graph and you replace each edge with 2 parallel edges, then of course you get a 6 regular graph, and Petersen conjecture can be stated that this 2G, which we usually denote this graph by 2G, that the chromatic index of this graph should be 6. Okay, so this is another way of looking at this conjecture. Now, I want to briefly discuss why this conjecture is easy or trivial for 3 colorable cubic graphs. Basically, it holds for 3 colorable cubic graphs because if a cubic graph is 3 colorable, then you are able to partition it edge set into 3 perfect matchings. So if you take or repeat each perfect matching 2 times, then you will have the cover that Petersen conjecture states. So for 3 colorable cubic graphs, it's easy. Now, the next easy or trivial observation is that Petersen conjecture implies Birch conjecture. Basically, if you have these 6 perfect matchings and you remove one of them, any of them, I mean, we don't care, then you will have 5 perfect matchings, and each edge will belong to at least one of the perfect matchings. So this is why Petersen conjecture is stronger than Birch conjecture. And though here I wrote 2011, but on April 23 of 2010, that day was Friday, and every Armenian will understand why up to now I remember the day. So on April 23 of 2010, I got an email. I got the first email from Giuseppe, where he was sharing with me his preprint, which was proving the following: that conjectures of Birch and Petersen are actually equivalent. Basically, what Giuseppe was able to do, he just assumed that every bridgeless cubic graph can be covered with 5 perfect matchings, and using that, he was able to show that the property guaranteed by Petersen conjecture actually can be achieved. So these 2 conjectures are actually equivalent. Now I want to move to another topic. This is the topic of cycles and even subgraphs. Basically, a cycle for us is connected to regular subgraph of G. Basically, what this means that connected, we understand that it should be 1 component. To regular means that each vertex has to have degree 2 in the graph. And subgraph, it means that like just a graph which is a part of G. So if you have a connected to regular graph, then we will refer to it as a cycle. And an even subgraph for us is just a subgraph such that each vertex has even degree in H. So if all your degrees are even, then such a subgraph is called an even subgraph. Now, what is a cycle cover? A cycle cover for us is a system of cycles which are not necessarily distinct, such that each edge belongs to at least one of the cycles. So basically here what we are trying to do, we are trying to cover the edge set of the graph with cycles. So a cycle cover is a system, and again I want to emphasize that it may not be a set. And the number of edges in this cycle we will refer as a length of the cycle, and the length of the cover will be just sum of the lengths for each of the cycles in the cover. So, and of course, what we are trying to do, we are trying to come up with cycle covers that have the smallest length for the graph. Here I want to present some other classical conjectures. Basically, the first of them is that any bridgeless graph, and I want to emphasize that this graph may not be cubic, just any bridgeless graph where degrees also may not be the same, so the graph may not be regular. That in any bridgeless graph there is a cycle cover such that each edge belongs to exactly 2 of the cycles from the cover. Before I move to the next conjecture, I want just briefly explain why people feel that this conjecture should be true. Basically, if you look at a 2 connected planar graph, just assume that you have some planar graph drawn in the way that edges do not cross on the plane. Then if you take just the perimeter of each face, then they together will form this cycle cover that the conjecture predicts. So that is why people feel that every bridgeless graph should have such a property. So the conjecture, more or less, what I want to say is easy for 2 connected planar graphs. Planar graphs will not be discussed in this talk, so those of you who have never heard of this, just ignore this, what I explained. Now, the next conjecture is the classical 5-2 even subgraph cover conjecture. Basically, what this conjecture states that any bridgeless graph, again, not necessarily cubic, contains 5 even subgraphs such that each of the edges of the graph belongs to exactly 2 of the even subgraphs. Roughly speaking, you can obtain this double cover by 5 even subgraphs. And there is this classical shortest cycle cover conjecture, which says that in any bridgeless graph, again, not necessarily cubic, you can find a cycle cover such that its length is at most 7/5 times E. Again, where this magic constant 7/5 comes from, of course, it is because of the Petersen graph, because it contains 15 edges, and the shortest cover it has with cycles, even subgraphs, is of length 21. So that is how this 7/5 arises. And by the way, the same is with the even subgraph cover conjecture. For Petersen graph, this 5 cannot be replaced with 4 or 3. So,
Vahan, what was this I of whatever this letter is? Calligraphic C or something? What is that?
It's a cycle cover. Basically, it is a list of cycles.
No, this I means the number, like it is equal to T, the way you wrote it.
No. It is the length of the cover, which stands for the sum of the lengths of each of the cycles in the cover.
Oh, okay, I see. Got it. Okay, thanks.
Basically, number of edges of C1 plus number of edges of C2 plus number of edges CT.
Yeah, that makes more sense. Thanks.
So basically, 7/5 and 5 from the even subgraph conjecture arise because of the Petersen graph. Like in the case of Birch conjecture, you get 5 because it cannot be covered with smaller number of perfect matchings. Now, I want to just present some small observation for you. Basically, 5-2 even subgraph cover conjecture implies cycle double cover conjecture, and I want briefly discuss why this is the case. This is because of the theorem that goes back to Leonhard Euler. Of course, our colleagues who work in classical part of mathematics know Euler's work very well, and I'm discussing this just to say that this outstanding mathematician has also some results in graph theory, and this is one of the non-trivial results that we teach students when we teach graph theory. So 5-2 even subgraph conjecture implies cycle double cover conjecture just because if you have an even subgraph, then you can decompose each edge set into edge disjoint cycles. So any even subgraph has a decomposition, such a decomposition. That is why if you have 5 even subgraphs that cover each edge twice, then if you decompose each of the even subgraphs, then you will have cycle double cover. And this is just a consequence of a result of Leonhard Euler. The next result is a result from 1992, which says that shortest cycle cover conjecture implies cycle double cover conjecture. Roughly speaking, what this means, if this 7/5 statement is true, then you can find cycles such that each edge belongs to exactly two of the cover from the you have taken. I remember that we discussed the proof of these only once in our seminars. I cannot remember the year, but I remember that once I read the proof of these and also presented in our seminars in the Department of Informatics and Applied Mathematics. So
as I remember, we even consider some generalization obtained by Mkrtchyan, something like that.
Okay. So you were present. That day you were present. Okay.
Okay. See.
Okay. All right. So basically, these two conjectures strengthen cycle double cover conjecture in two different directions. Now I want to present some diagram for you. On the left, we have Petersen conjecture and Birch conjecture, and the row between them just means that they are equivalent. And on the right, we have three vertices or three blocks which correspond to the conjectures, and each of them implies cycle double cover conjecture. And the sad part with my diagram is that somehow they are not related. So these two topics are not related. So it's a bit. I think it's not good. It's not good, and this is the main motivation why I will consider the next conjecture, which will somehow unify these conjectures. In order to present the main statement, the main conjecture of my talk, let's introduce some more definitions. So if you have a vertex, then this partial sub G of X, I hope I am pronouncing it correctly, will denote the co-boundary of the vertex X. Sometimes it's called co-boundary, which stands for the set of edges that are incident to the vertex. Basically, the cardinality of this set is just the degree of the vertex. Now, if you have two cubic graphs G and H, then an H coloring of G for us will be a mapping from the edge set of G to the edge set of H, such that each vertex is colored by some edges of the graph H, and these edges should form a co-boundary in the graph H. Basically, what we are doing here, let me discuss this a bit more in detail. So usually when you are coloring, you do not have any kind of restriction on the set of colors. They can be anything. Now here we are restricting the set of colors as we want them to be edges of another cubic graph H. And an H coloring for us is just a type of coloring such that three pairwise adjacent vertices that are adjacent to the same vertex are colored by a similar triple of edges of H. Okay, so it could be a bit confusing, but I have presented an example for you, so I'm going to discuss this in detail. So if G admits an H coloring F, so if you manage to color G with H, then I will write H proceeds to G. Roughly speaking, this will say that G admits an H coloring. So H proceeds to G stands for G admits an H coloring. Now let's discuss one example in detail so that you see what does this H coloring mean. On the left, we have the complete graph on 4 vertices, and I have labeled the vertices with 1, 2, 3, 4, and the edges of H are A1 to A6. On the right, we have another complete graph, in a sense that, of course, this is not a complete graph as I defined before, but this is a complete bipartite graph, so another type of complete graph. It is again 3 regular, and its edges are colored with A1, A6, and the labels for each vertex stand to the following. It stands for the following: what is the vertex that it corresponds? What is the vertex from H that it corresponds to? More precisely, let's look at the two vertices on the left of the graph G. Basically, as you see, its edges are colored with A1, A5, A4. This is a proper coloring in a sense that adjacent edges have different colors. Moreover, A1, A5, A4 form the co-boundary of the vertex 1 in H. As you see, these two vertices are colored by the triple of edges incident to the vertex 1 in H. Similarly, if you look at the graph of the two vertices of graph G in the middle, which are labeled with 4, then they are colored with A1, A4, and A6. And if we look at H, then A3, A4, A6 form the co-boundary of the vertex 4. So these three vertices are colored by the triple of edges incident to the vertex 4. Finally, if you look at the right, then these two vertices, which are labeled by 3, are colored by A2, A3, and A5. And A2, A3, A5 for the co-boundary of the vertex 3 in the graph H. And these three edges are colored by these three edges incident to 3. So that is why this example is shows that our graph G admits an H coloring, and hence we can write H precedes G. Now I'm going to discuss some properties of this type of coloring. First, the property, the binary relation between cubic graphs, this precedence relation that we discussed. Basically, if we have that H precedes to G and K precedes H, then K precedes G. What does this mean? If you are able to color G with H and H with K separately, then you can color G with K. And why this is true? Because if you consider the classical composition of functions, if you look at the coloring as a function, if you look at the composition of the functions, then you will have the proof of this statement. That is why this precedence relationship is a transitive relation. Another property of this relation is the following: that if you have arbitrary 3H colorable cubic graph like K4, like the complete bipartite graph on the right of my slide, previous slide, or any other 3H colorable cubic graph, then you can color it with any cubic graph H that you would like to. Okay, so any 3H colorable cubic graph admits an H coloring for any cubic graph H. And why this is true? Because because if your cubic graph is 3H colorable, then you can do something very silly. You can fix one vertex, one of them. You can take your colors as the edges incident to this vertex, and you are done. Because if you have a 3H coloring, then you can color with these three colors. So 3H colorable cubic graphs represent the easiest case of these H colorings somehow. Another property of
Vahan, sorry to interrupt you. Any chance you can show me again the definition of this squiggly less than relation on the 2 slides ago?
Yes, sir, on this one.
This one, yeah. So I just want to see the condition on your function. So, yeah. So okay, you just map edges to edges, and then
each triple incident to a specific vertex must be colored by a similar triple from H.
Okay, there is no condition on the function though. I'm sorry, there is no coloring or like homomorphism condition on the function. So nothing like it's not a homomorphism. It's not a graph homomorphism.
No. If I'm trying to understand what you mean by homomorphism of graphs, but I just want the following: that 3 edges incident to the same vertex are colored by 3 edges of a graph H of some 3 edges incident to some vertex. Basically, if you are moving from one vertex to another vertex of G, this vertex of H may change.
For example, okay, yeah.
let's look at our example.
Moreover, some vertices can be missed, for example, as I see.
Yeah. For example, on this figure, on the two vertices on the left are colored with triple of edges incident to the vertex 1 of H. The two in the center are colored with 3 edges incident to the vertex 4 of H, and the two on the left are on the right, sorry, are colored with triple of edges incident to 3. And as Petros said, the 2 is fictive somehow. The vertex 2 is not present.
Okay. All right. Yeah. Got it. Thanks.
So basically, in this coloring, some vertices may be fictive, some edges may be fictive, and we just want a triple to be colored by some triple.
Okay, but the definition works in general, not just for cubic graphs. Like it's a general definition.
Yeah. It's a general definition, but
yeah, I got it. You're using it for
cubic graphs form the core and probably the most important case of all this mess.
I actually have a question. So can you go back to that example? So would you say that this definition is equivalent, saying G has a subgraph such that, H has a subgraph such that G has a blow up of it? Because right now, if like you actually took 1, 3, 4, right, the triangle, like 2 wasn't included, and you blew it up, and it became the G. That's what you were able to do. Is that okay?
Maybe for this, yes, but my G might be larger. I mean, it may contain some 100 vertices, and I still can do something like this. No one says that you have to use all vertices of H or all but one. I mean,
that's why I'm saying a subgraph of H, but you have to cover all the edges, all the vertices of G, right?
Yes, you have to color all the edges of G so that around each vertex of G you have colors. You have triple of colors incident to to some vertex in H.
Also, Liana is not a subgraph because the edge A6 is used. So if you remove 2, that edge would disappear. Same with A2.
Oh, wait a second.
So the edges are used, but maybe the vertex isn't.
Yeah.
Okay. Yeah. Sure.
Okay.
Now, one important. This example is a bit of something like a difficult edge coloring of G. But what I wanted to say that for 3H colorable cubic graphs, you can do something very silly. You can take just one vertex and map everything to this vertex, to the edges incident to this vertex. That is why 3H colorable cubic graphs admit an H coloring for any H you would like to. And this shows that you do not have, how you say this, basically,
basis.
This is not an order somehow. The relation it's transitive, but it is not an order, because if you take two 3H colorable cubic graphs, then you can always color one of them with another one, and they may not be isomorphic or something like this. So that you can have structurally different cubic graphs, which one of them can be colored the other one. So this is not an order somehow. That is why basically if you put all equivalence in one class, then only after that you are going to get order. All right. Basically, I want to formulate one statement that somehow shows that you can somehow have a restricted version of the definition. If your graph G admits an H coloring, then of course 2 adjacent edges will be colored with adjacent edges in H. What I'm trying to say that adjacent edges of G will have adjacent edges of H as a color. Okay, it turns out that the converse statement is not true, but this is only this type of thing happens only when H has a triangle. So if you forbid triangles and you assume that H is triangle free, basically there is no cycle of length 3, then if you are able to achieve that any adjacent edges are colored with adjacent edges of H, then you can easily show that this type of coloring is an H coloring of G. Okay, so in the definition we have triples of edges, but you almost always you can work with just pairs of edges when H is triangle free. Okay, see, this somehow might be important for you. Okay, now I'm going to state and discuss very briefly the following lemma, which provides some kind of motivation why H colorings of cubic graphs are discussed. Okay, so let's assume that we have two cubic graphs G and H, and let's assume that F is an H coloring of G. Now it turns out that it has some properties, and first of them just says that if you have taken arbitrary matching of H, recall that matching is just an independent subset of edges, then its pre-image is going to be a matching in G. And why this is the case? Just because it is just a restatement of the previous thing. I mean, if adjacent edges are colored with adjacent edges of H, then this means that the pre-image of any matching is just matching in the original graph G. Okay. Now, if let's assume that you are able to find a TH coloring for for your cubic graph G. Now, if you look at the pre-images of these color classes, basically a color class is the subset of edges that have the same color. And if you for each of the color classes, if you consider its pre-images under F that you have, then you are going to obtain a coloring with T for G. Okay, if you have a coloring for H and you take its pre-images, then you are going to get a coloring with the same number of colors for G. That is why the chromatic index of H is an upper bound for the chromatic index of G. And since for cubic graphs, probably you recall the theorem that I discussed, chromatic index can have value either 3 or 4. This statement B, roughly speaking, means the following: if your cubic graph G is not 3H colorable and the cubic graph H is 3H colorable, then you cannot color G with H. Okay, so roughly speaking, the essence of this statement B is that. Now, let's assume that the matching M in this statement A that you have taken is a perfect matching, that it covers all the vertices of H. It turns out that its pre-image is going to be a perfect matching, and the proof of this requires some effort, but it's not very difficult. And it implies a statement similar to B. Basically, the smallest number of perfect matchings that you need to cover H is an upper bound for the same parameter for G. Okay. Now it turns out that this definition implies certain things not only for matchings, perfect matchings, but also for cycles and subgraphs. So if you have an even subgraph C in your H, recall that H is the graph whose edges are colors for us, then the pre-image of every even subgraph is going to be an even subgraph of G. Okay. This immediately implies that if you have a bridge in your graph G, that then its color has to be a bridge of H, because I mean, if your bridge has received a color that lies in a cycle, then the pre-image of this cycle should be should contain a cycle, and since it is a bridge, it cannot lie in a cycle. Okay, so that's why bridges of G must have a color that is a bridge. And of course, this implies the last property that if you have a bridgeless graph, then G must also be bridgeless. because if it has a bridge, then we cannot find a color for it. Okay, so more or less, this is the most important lemma for that stands somehow behind the definition of H coloring sub G. Now I want to present some.
Vahan, may I make a remark slash question? So basically, this is what I meant by a graph homomorphism. I meant that the line graph, by which I mean, the graph whose vertices are the edges, and the edges are connected if they're incident in the original graph. I think that's called the line graph, right? Right. So what you're saying is that this relation means there is a line graph homomorphism. It implies it, but it's not equivalent. It's only equivalent, as you said, for triangle-free graphs. So for triangle-free graphs, this relation means exactly that they have a line graph homomorphism. Like
yeah, but I'm just trying to understand what you mean by a homomorphism in graphs.
Homomorphism of graphs. That means it's a map from for homomorphism for two graphs. It's a map between vertices, such that the edge on the left is mapped to the edge on the right, but not necessarily vice versa. So this is a homomorphism of line graphs, and it is it depends only if your graph is triangle free. And then this whole lemma just follows from the fact that all these properties transfer for graph homomorphisms on the level of edges. So on the level of the line graph, for the line graph. Anyway, it's just easier for me to think about it that way as graph homomorphisms, so that these statements are just natural.
Okay. This is nice that you decided to join the seminar. All right, because I never thought in the language of homomorphisms. So okay.
Well, yeah, sure.
Right. All right, let's move to the consequences of this lemma. Why the author of this definition? Why he has defined this. So. Basically, the author is the following person who, in 1988, presented the Petersen coloring conjecture. Unfortunately, he's not alive. He was from France. Basically, he presented a conjecture that has unified these conjectures from 70s about perfect matchings and cycle covers, which were even posted even before. So the Petersen coloring conjecture from 1988 says that no matter which bridgeless cubic graph you take, you can color it with a Petersen graph. Those students who have had a chance to work with me, usually when I introduce these concepts to them, I refer to this precedence relation as like the graph on the right has somehow easier structure than the graph on the left. Okay. So the graph G is easier than the graph H if G admits an H coloring. Now, this conjecture usually, I explain that the Petersen graph is the worst example that you have. And I hope you somehow agree with this, because when you look at the parameter K, Petersen graph is the smallest graph for which K is 5. If you look at this 5 to even subgraph, then Petersen graph achieves again this constant 5. And if you look at the 7/5, then its length of the shortest cycle cover is 21, which achieves the bound 7/5e. So somehow I hope you agree that the Petersen graph is the worst example somehow. And I will discuss one more conjecture later, for which again Petersen graph is the smallest example for which the bound is tight. So somehow there is motivation that behind this conjecture. Okay. So Petersen graph conjectures predicts that any bridgeless cubic graph has to be colorable by the Petersen graph. Let's quickly discuss some kind of consequences of the Petersen coloring conjecture. Clearly, Petersen coloring conjecture implies Birch-Walkerson conjecture, and why this is true? Because if you take arbitrary bridgeless cubic graph and you are able to color with Petersen graph this graph G, then if you consider the pre-images of each of the perfect matchings of the Petersen graph, which had 6 perfect matchings, then of course by the lemma you will get the corresponding cover predicted by the Birch-Walkerson conjecture. Okay, so just blindly take pre-images of the each of the perfect matchings of the Petersen graph. Now, next, Petersen coloring conjecture implies 5-2 even subgraph cover conjecture. And why this is true? Because if you take the pre-images of the 5 even subgraphs of the Petersen graph, for which you achieve 5-2, it can be shown that you will achieve the same property for your arbitrary graph G that you have taken. And finally, more or less by a similar thing, you can prove that if Petersen coloring conjecture is true, then you can find a cycle cover of length 7/5e for any bridgeless cubic graph G. Just some more or less blindly recover the details from your Petersen coloring conjecture of your arbitrary bridgeless cubic graph G that you have taken. Okay. So, if roughly speaking, this conjecture says that if you were able to color with the Petersen graph, then all these magical properties you can extract from your Petersen coloring of G. Now you see that our diagram has become more interesting in the sense that they are related, and the main conjecture that connects everything is the Petersen coloring conjecture. Now, this is where my general historical and some kind of graph theoretical overview ends. And now I want to move to the topic of my paper with Giuseppe. And first, I will introduce normal edge colorings. Basically, I want to discuss the notion of snarks. Some of you may have heard of this. Those of you who haven't, I just want to say that snark is a term introduced by Lewis Carroll. I don't know whether you like Alice in Wonderland, but it was one of my favorite cartoons, especially the one made in Soviet Union, in Ukraine. And I even watched that in 2010 in Germany when I was a researcher. And I remember that Anush did not like this, but in any case, snark is a concept that comes from the poem or novel of Lewis Carroll, Hunting of Snarks. So what is a snark? A snark is a bridgeless cubic graph that is not 3H colorable. And Petersen graph is the smallest snark somehow. Okay. Now, in the second half of 2010, when I was already back from Germany, I was going around some statement, and basically I was thinking about the following. Let's assume that we have a cubic graph, and for which we were able to find a Petersen coloring such that some edge is fictive, in a sense that it has not become a color of some edge. In other words, you manage to find a coloring of your G such that one of the edges is not used. Okay, and I was just trying to prove that such a cubic graph has to have an easy structure, in the sense that it has to be 3H colorable. After making some attempts, I failed to do that, so I decided to send an email to my colleague from Germany who hosted me in 2009-2010, and he replied that basically this is going to be a very difficult statement, and like Petersen coloring conjecture, I mean, it should be very difficult one. So this was the content of his first email. So I logged out from my Gmail, and after some hours, I again went to check my email. There was the second email from my colleague, and as it happens in research, basically he was very quickly able to refute himself by proving that such a graph has to be 3H colorable. So this statement arose as a result of this email exchange, and roughly speaking, this means that basically what this simple observation implies, that if you have a snark, and the snarks form the core of all these conjectures that we discussed, basically in any Petersen coloring, you must use all edges of the Petersen graph. In other words, you have to find a coloring using 15 edges of the Petersen graph. And to my mind, this is horrible. I mean, you have to, I just don't understand how one is going to see this coloring with 15 edges. Okay, I mean, how a human being will come up with some algorithm with 15 edges. I mean, this is horrible. And to my mind, this was the main reason why the author of the Petersen coloring conjecture has introduced the following type of colorings. Basically, let's assume that we have a KH coloring. This is a proper coloring, so that again adjacent edges receive different colors. And S sub FW, let be the spectrum of the vertex W. Basically, what is the spectrum? It is the set of colors that the vertex W sees. Basically, what are the colors that are incident to this vertex? Okay. Now, if you have a cubic graph, then each edge is adjacent to 4 edges. So let us say that our edge UV is poor if the union of spectrum of U and V is exactly 3. What does this mean? That basically around U and V, you see the same 3 colors, okay? And let us say that this edge UV is rich if together they see 5 colors. Of course, since you have 5 edges and your coloring has to be proper, then the smallest number of colors that U and V can together see is, of course, is at least 3 and is at most 5. Basically, when I discuss this definition with colleagues who are not working on this topic, they say that in this definition, basically, you do not like the case 4, okay? So we just do not want our coloring to have an edge whose such that its at points together see 4 colors, okay? And and as a result of this, let's say that KH coloring of a cubic graph is normal if any edge is either poor or rich. In other words, this case 4 does not appear in this coloring, okay? Now, and as usual, it happens with colorings when you have introduced some specific type of coloring, it is natural to consider the smallest number K such that you can color your graph with these colors. So chi sub and G stands for the smallest K for which G admits a normal KH coloring. Of course, for cubic graphs, this number is at least 3. And you can easily see that it is exactly 3 if and only if the cubic graph is 3H colorable. Okay. Now, what is, oh yes, I want to discuss one example of a normal edge coloring because this will be important for us. So if you have this cubic graph, basically what I have taken, just see that the 2 parts on the left and the right are just the complete graph on 4 vertices. We have just taken one edge. We have replaced this edge with the path of length 2, and the 2 degrees, the 2 vertices of degree 2, which are V1 and W1, are joined by one edge, so that we get a cubic graph. Okay. So in this figure, I have presented a normal 7 coloring for this cubic graph. You see that it has only one bridge, which is V1 and W1, and this bridge is poor. Why it is poor? Because V1 sees the colors 1, 2, 3 in this coloring. W1 sees 1, 2, 3. So together they see 3 colors. That is why, guys, just a second. Maybe I am run out of. Just a second. Oh, yes. Okay. Are you able to see the figure?
Yes.
Okay. Sorry, my battery was dying. All right. So bridge. The only bridge of this graph is poor, and as you can see, the remaining edges are rich. For example, let's look. I don't know, V4, V5 on the left. V4 is incident to colors 1, 4, 7, and V5 is incident to 6, 1, 5. So together they see 5 colors. That is why this edge is rich, and actually you can just verify that the remaining edges are rich. That is why this is an example of a normal 7 coloring of this graph. And actually in our paper with Giuseppe, we were able to show that if you take any cubic graph and apply this operation, basically replace just one your edge with a path of length 2 and attach this structure with the K4, then the resulting cubic graph is going to require at least 7 colors in any normal coloring. All right, so you can construct infinitely many cubic graphs for which the normal chromatic index is at least 7. Just attach this K4 with a subdivided edge to any cubic graph, and you will have such an example.
One question.
Mm-hmm.
Any strong coloring, it's in fact normal, yes?
Yes.
Okay, I see.
I'm going to use that observation next. So
okay.
So this example, this graph has normal chromatic index 7, and one can construct lots of examples, infinitely many cubic graphs that require at least 7 colors. Now, in 2016, when I was visiting Giuseppe in Modena, we were just discussing some topics that we could collaborate. And one of the questions that we addressed is the following. Basically, does any cubic graph admit a normal KH coloring for some K? Okay. Of course, you can color every edge with a new color. That is why it is expected that you should get a normal coloring. So if your cubic graph is a simple cubic graph, basically there are no parallel edges, of course this approach works. And it's not hard to see that you can construct a silly counterexample for this approach of coloring by just taking one edge in a triangle to have multiplicity 2. This is why such cubic graph cannot have normal coloring, no matter how large K you take, because you have 4 edges, so you are always going to have 4 different colors around these parallel edges. That is why there is a silly counterexample to this approach. Luckily, this is the only this type of examples are only these examples. That is why if you stick to simple cubic graphs which do not have parallel edges, then of course they admit normal K coloring for some K. And a natural question is to understand how small we can take this K. Basically, in his paper in 1988, the author of the Petersen coloring conjecture basically proved a nice proposition that your cubic graph admits a Petersen coloring if and only if its normal chromatic index is at most 5. Okay, roughly speaking, he says that Petersen colorings and only they correspond to normal 5H colorings. So somehow you see that this proposition overcomes the property that I was trying to achieve with my colleague from Germany. There we showed that if you go directly to the definition of H colorings, then you have to color with 15 colors your bridgeless cubic graph if you are trying to prove this Petersen coloring conjecture. And now he says that you can stick to 5 colors, but you have to make sure that you are going to get normal coloring. So it is not a standard coloring. Okay. So proving on upper bound 5 for bridgeless cubic graphs implies the Petersen coloring conjecture, and actually it is just a restatement of the Petersen coloring conjecture. All right. So another way is to prove the Petersen coloring conjecture is to obtain an upper bound 5 for the normal chromatic index. Now, this is where our result with Giuseppe comes. Basically, we discussed the following question. what is the smallest k such that any simple cubic graph can be colored with k colors in a normal edge coloring. All right. In other words, what is the constant k that we can upper bound the normal chromatic index of arbitrary simple cubic graph G? Note that here there is no restriction on the cubic graph that it has to be bridgeless. It may contain bridges. Okay. So basically, when we were discussing with Giuseppe, of course, we were trying to prove something. Also, we were looking in the internet. So as you see, by this discussion of K4 attaching to arbitrary cubic graph, one can show that there are arbitrary large examples that require at least 7 colors. So no matter how large cubic graphs you take, there are cases where you need 7. Also, we digged in the internet and we saw that Anderson in 1992, basically using the observation that Petros mentioned some minutes ago, that actually strong colorings, which are edge colorings in which every edge is rich, basically you do not have a poor edge. Strong colorings are, you can find a strong coloring of any simple cubic graph with 10 colors. So this result we encountered in the internet. So it was published in 1992. So this approach implies that in our question, our bound is at most 10. And after some more investigation or research in the internet, we noticed that our colleague Robert Jamal from Prague and his student in 2012 proved that actually this 10 can be replaced with 9 if you are working with normal colorings. Unfortunately, he sent the master thesis of his student. This second author is a female student, and her master thesis is written in Czech, or maybe I'm wrong. It was the bachelor thesis. In any case, basically they proved that any simple cubic graph admits a normal coloring with 9 colors, and the proof was in Czech. So it was absolutely hopeless for me and Giuseppe to understand the proof. But in his email, Robert Jamal stated that basically what they did the following. They took the proof of Anderson and tried to save a color, and actually they succeed. Okay, so this 9 arrives just if you are looking with normal coloring, so you are okay with poor edges, you can modify the coloring of the Anderson so that you get normal 9 coloring. By the way, those of you who are inside graph theory, I just want to let you know that this Anderson is the same person from Sweden who is the co-author of Anderson-Goldberg-Stigmund conjecture. Okay, we will not need this conjecture, but this is just for the sake of information for graph theorists. Okay, so basically Robert Jamal and his student managed to obtain a 9. So somehow there was a room for us, because Robert stated in his email that they do not have an example of simple cubic graph that requires 9. And when I was visiting Giuseppe in the autumn of 2017, basically, during this 1-year stay in Verona, we managed to prove that this 9 can be replaced with 7. I hope you see that this 7 is tied for infinitely many cubic graphs, so there is no further improvements that can be made. And this is the main result that I got with Giuseppe. And the remaining part of my presentation, I want to briefly discuss with you how this magic constant 7 arises in this coloring. I mean, what is this 7? I mean, what it corresponds to? And since Armen in his email stated that he would like somehow our talks to provide some kind of relationship with other areas, I work a bit hard during past weeks in order to make sure that at least the big picture of our proof is clear, and you will see that somehow we are getting some interesting connections with algebra. Okay, and this constant 7 stands for something very important in algebra. All right.
Vanja, I have to go make lunch for my little daughter, but thank you so much for a very interesting and, shall we say, colorful talk. I'm looking forward to the next one.
Thank you. Bye.
Bye.
Also, Fahan, what if we kind of stop at this moment, because it's an interesting point that you're making, and continue next time, because people might have questions and some things like that. Seems like it's a good point to stop at 7:20.
Armanjan, you are the organizer, and I'm willing to follow. Your guidelines. I can present the remaining part next time. And if we are done earlier, I can start the second presentation. Otherwise, I can present on September 24 also.
Yes. What if we do like that, and there's never a problem having a third talk if you don't make it in 2 talks? So it's just the timing, people start leaving, something like that.
All right. I'm completely okay with this approach. If all of you are okay, we can stop here and continue on September 17th, 6 p.m. Armenian time.
And Petros is not is maybe out, but maybe I ask if there are any questions or comments.
Yes, sorry.
Please, Petros, go ahead.
1 second. Yes, maybe someone has a question, comments, remarks.
In the chat, there is something. Maybe you can look what is written there.
Yes, mainly the people saying about living.
I actually have a question. So this normal edge colorings are defined for only cubic graphs, is that right?
Basically, first it was introduced for cubic graphs, but there are papers where people are extending it to higher regular graphs, and even to graphs that are not regular. Basically, they have not the 2 vertices that have different degrees. For example, unfortunately, my situation was not very good this past year because of the birth of my son. So I was in a terrible situation, but finally I was able to find the time and read the recent preprint by Giuseppe and his PhD students. And basically, Giuseppe was extending these edge colorings to high regular graphs, and so, and even not, if I recall correctly, there were 2 vertices of not equal degree. So people are working on
okay. How that extension would be? Is it like maximum degree +2 and maximum degree -1? Like, what is the definition of poor range there? Let's say for regular graphs.
Basically, normal colorings. You can, for example, if you want edge colorings, then Giuseppe was basically requiring the same thing, that the co-boundary of each vertex is colored by a co-boundary of edge. In case of normal colorings, if let's assume you have a K regular graph, then your edge and its adjacent edges together have 2K minus 1 edges in total, yes?
Yeah.
Now you can define poor if the spectrum of 2 of these vertices is K, and you can define A as reach if it is 2K minus 1. And anything, and you don't like anything in between, like it was 4 in case of cubic graphs.
I see.
For example, one of my colleagues from Poland in my seminar presented this way of definition, but I'm not aware of any papers or even preprints on this. Okay, so this is something like a direction that one can try to go.
Yeah, definitely. Okay, that was it.
Okay, other questions? Okay, so maybe we just say thanks our speaker. Thanks, Juan.
Okay,
Thank you
very much for joining.